Okay, this is a simple demonstration of how sound waves interfere with each other. I'm going to use for this MATLAB, but you don't have to know anything about MATLAB to follow along. So let me just open it and clear this thing. So the first thing I'm going to do is read some audio data inside MATLAB. So I'm going to create two variables. Variable Z, where I'm going to store my signal, and variable Fs, and which stands for frequency of sampling. MATLAB is going to read the audio, put every single channel inside this variable Z, and infer what the sampling rate is, and put into this variable Fs. So the way we do this here is audio read. And now I'm going to, this is a string, so I'm going to use Dropbox. It's a file inside my computer. Dropbox, samples, household. And this file is called bottlepops.aif. Okay, and I'm going to put a semicolon here so that MATLAB doesn't display all the samples within this file. There are many. Okay. So I've now created these two variables, Fs and Z. So Z has the length 356,328 samples by 2. By 2 means this is a stereo file. And 44,100, this is the sampling rate. Now, something I like to do here, I don't need both channels here, so I'm not just going to declare Z as just the first channel. Okay. Now, this is how this variable Z looks like. So let's just plot this thing. And so there are 3 bottle pops here. See, the maximum amplitude is normalized between 0 and 1 in the digital world. The maximum amplitude here is just a little above 0.5. There are 3 transients and 4 times 10 to the 5th power samples, which is this number here, 356,328, approximately, obviously. So now let's hear this thing. So we can, to hear this, just put sound and then Z and the sampling frequency that we want. And okay, these are the 3 bottle pops. And what else? So I can certainly infer the duration of this file. The duration of this file is the length of that vector Z, right? Which we know is 356,328. Okay. And we can just get that and divide by the sampling rate, and we'll see how long this thing lasts. So it lasts a little over 8 seconds. Okay. Now, I'm going to go ahead and declare another variable here. Let me just use this thing. So now I'm going to put this in a different variable, W, and this one is called alarm warning. Okay. And go ahead and read this thing. We can see how it looks. Just let's plot W. So this is how it looks. Oh, by the way, this is showing both channels. In orange, you see the left side probably, and in blue, you see the right side. So let's do the same thing we did before. So let's just say that W is going to be just the first channel. So all the samples, but only the first channel. Okay. And semicolon. Now we can, when we plot W here, we'll only see the blue one. Okay. Now, so this is just an alarm warning, and there's just one big transient here, a big chunk of sound. It isn't so loud here. Well, usually alarms are pretty loud, but it isn't so loud here. It's definitely softer than the bottle pops. But let's hear this, and it might be more conspicuous though. So sound and W with this frequency of sampling. Okay. Now what I really want to show you here in this tutorial is this. We can get our vector Z and just evaluate each sample, like sample number 100,000. Right, and MATLAB is going to give us the value here. Okay, so, and we can get a range between 1, let's say, and 16. Okay, and we get this range here. They're pretty soft at the beginning here. And we can do the same for W. Okay. Now, something else we can do is add these two things, Z from 1 to 16 plus W from 1 to 16. So we're pretty much just adding vectors here. So you'll see that we get 0.005 plus what is this, 10 to the minus 3 times 0.1221. So our result here is 0.0006. Okay, and this is an approximate result, minus 0.0001 plus 10 to the minus 3 times 0.0916 is going to give us roughly 0. Okay, so what we're going to do now is take just the first 164, 567 values of Z so we can add these two vectors together. So we're going to do this by taking Z from 1 to 1, 6, 4, 5, 6, 7, and we're going to add this to W. Okay, and let's just call this maybe signal S. Okay, and you go. Now S is a vector that has the same size, the same length as W, and consists of the sum of these two things. So if you take Z from 1 to 4 and W from 1 to 4, then S from 1 to 4 is going to be the sum of these two things. So 0.1221 plus 0.4578 gives you 0.5798. Okay. Now let's go ahead and plot this signal S so we see how it looks like. Now we can see that there is a big, remember that this signal W here went just up to 0.3 in amplitude, whereas the bottle pops were a little louder. Now you see that when we add, we just get these two things superimposed, right? Plus we get another bottle pop here toward the end that wasn't in signal W before. Now how do you think this is going to sound? Well, let's check it out. So sound, signal S, and the sampling frequency, and voila. Again. So in short, just by adding numbers, our ear is able to separate these two sound events completely by simple addition.